In this video I'm going to show you how to connect a NRF24L01 plus transceiver to a Raspberry Pi. More specifically, I'm going to show you how to connect two of these transceivers to two different Raspberry Pis. What you're going to need to complete this tutorial, of course, is two of these transceivers and two Raspberry Pis. This Pi here is a model Raspberry Pi 1 Model B+, and this Raspberry Pi here is a Raspberry Pi 2B. So two different Raspberry Pis, both running the Jessie operating system. These rules should apply to other operating systems as well. And in addition to that, you're going to need a way to be able to connect these transceivers to the Raspberry Pis. I have brought out the headers onto a breadboard here using these cobblers, and I have jumper wires to connect it all together. So let's get started. Different transceivers may have different pinouts. Mine here happens to have the pinout label on the back, and you may have to check your data sheet for your pinout as yours may vary. VCC is connected to 3.3 volts, ground is connected to ground, CSN is connected to CE0, which is GPIO 8 or pin 24, CE is connected to GPIO 17 or pin 11, MOSI is connected to the MOSI pin on the SPI bus of the Pi, that's GPIO 10 or pin 19. SCK is connected to SCLK on the Pi, GPIO 11, and MISO is connected to GPIO 9. We will not be using the IRQ pin, that is the interrupt pin. So let's get started in wiring this up. Once that's all done, be sure to wire your second transceiver to your second Raspberry Pi. After we have wired our transceivers up to our Raspberry Pis, we're going to have to download some packages and start writing the programming needed to establish some communication. So what I have here in front of me is a desktop of the Pi that will be receiving our message. I have the desktop of our Pi that will be sending our message, and then I have loaded instances of the terminals I'm connected to my Pis headlessly here. So what I'm about to do is set up one Raspberry Pi and download some packages on that Raspberry Pi, and these steps need to be done on both Raspberry Pis. So let's get started. First thing we're going to want to do is enable the SPI bus on our Raspberry Pi, and you do that by typing in sudo raspi-config. Go down to advanced options, SPI. Would you like to enable it? Yes, you would. It's been enabled. Great. Would you like it enabled by default? Yes, you would. Great. And then we can finish. Okay. Next, we're going to have to update our Raspberry Pi. So sudo apt-get update. Now that we've updated, we're going to have to install Python packages that allow us to access our SPI. And so the way you go about doing that, you need to do this for both Raspberry Pi, Python 2 and Python 3. And the command you use is sudo apt-get install. If you're using Python 2, python-dev. If you're using Python 3, python 3-dev. And yes, we want to install them. So I already have these packages installed, so this doesn't take me very long. This could take you a moment. Next, we're going to have to download a package, and we go about doing that by typing in wget https://github.com/gadgetoid with a capital G /pi-dev/archive/master.zip. This downloads a package called master.zip. You can see that here. We're going to want to unzip master.zip, which creates this folder, pi-spi dev-master. Let's clean up, so let's get rid of that master.zip file. And now let's navigate to our pi-spi dev folder. Now we're going to have to make this for both Python and Python 3. And so type in, let's start with Python 2. So python setup.py install. And now repeat the process for Python 3, so sudo python 3 setup.py install. Again, you don't need to do this for both languages. If you're following along in 3, you need to do the Python 3 steps. If you're following along in 2, you need to do the Python 2 steps. This needs to be done. So far, everything we've done needs to be done on both Raspberry Pis. Let's navigate back to our root folder, and then let's go into our desktop. And in our desktop, we're going to create a folder called NRF24L01 and navigate to that folder. Now we're going to install another package, so git clone https://github.com/b-l-avery/lib_nrf24. And what this is it's actually a package of files with some examples in there, so really you could stop following the tutorial now because you really have everything you need. But what's really important here is this file here. This file here allows you to access the transceivers in Python, and Python is such an easy language to work with. That's the reason why we're going to be doing this all in Python. So let's copy that file. You could just go ahead and get started with the examples, but I'm going to write from scratch so you guys can follow along. Let's just copy that file to our root folder, the NRF folder on our desktop, I should say, rather. And so now we have the libnrf24.py file in our NRF24L01 folder. Now we can get started on writing our scripts in Python. So since I've been doing this all on the receiving Pi here, I'm going to open up on the receiving Pi. Here's that folder, and inside that folder I'm going to open up idle3 on the receiving Pi. And we're going to write a new file. Alright, so first things first, we're going to have to import some packages. We need to import packages that allow us to access the GPIO header of the Pi, so import rpi.gpio as GPIO. And then we're going to import from that module lib_nrf24. We're going to import NRF24, which is what's going to allow us to access the transceiver itself. We're going to import time while we're at it, and finally we're going to import the SPI so that we can actually access it. We're going to set up the GPIO such that it is BCM, so GPIO.BCM. So that is when I say GPIO 17, it actually points to GPIO 17 and not the actual pin, like pin 17. We're going to have to create a set of pipes here. And what the pipe is kind of like an address, and it has to be an array of bytes, and this is the address that you associate with your transceiver, or I should say it's like the kind of like the address that when you are communicating on a certain bandwidth or a certain channel that you can differentiate your different devices. So we're going to be typing in 0xE7 5 times here. So that will be one address, and that could be the only address that we use right now, but since this tutorial will be leading into the next one that shows you both how to send and receive instead of one-way communication, I'm going to preemptively assume that you're going to be watching that video and set up a second address. Alright, excellent. So we have our two addresses set up here. Oh, let's actually give this a save. So save this as, I'm going to save it in that desktop folder, NRF24L01, and I'm going to call it receive.py, since this will be our receiver. Okay, so this is going to seem like a lot because this is how we initially set up the radio, but it's really not that bad. So first we're going to create an instance of our radio, and it's going to be part of like the NRF24 module. So we need to pass in the GPIO and the SPI. And then we're going to turn on our radio, or rather I should say we're going to begin our radio. And you know how I said we wired it up to CE0 and GPIO 17. That's your That's your CSN and CE respectively. So if you wired it up like I did, great. Those are the values you put in. If you wired it your own way, then you're going to have to accommodate accordingly. Next, we can now set up a whole bunch of like different options. So for example, we can set our payload size, and we're going to set our payload size to be, that's a capital S, we're going to set our payload size to be 32 bytes. We can set our channel. Obviously, the channels have to match between the two Pis. So I'm going to choose channel 60 here. So we're going to be connected on channel 60. And then we can set our data rate. The higher the data rate, obviously the faster your transmission speed, but the riskier it is for long distance communication. Now, since this is all sitting on my desktop here, I think we'll be able to get away with our 2 megabit data rate. We're also going to have to set the power level. So set the power amplification level, and this is important if you're, say, running on a battery. You don't want to be burning all your juice, so I'm going to say minimum, and besides they're like literally 4 inches away. I don't need to max out the power right now. And you can poke through the lib NRF24 and you can figure out what all these different options are. So we can also set up a auto acknowledgement. So, oh, why am I tabbed in here? We can set up our set auto acknowledgement, and we want that to be true. I need to close my bracket there. We are going to be able to set up, say, enable dynamic payload sizes. And we're going to want to enable our acknowledgement payload. And now we can finally open up a reading pipe. So this is the receiving end, and as a receiver we're going to be reading whatever's coming to us, and that's why we're opening up a reading pipe. As you can imagine, on the sender we're going to want to open up a writing pipe. So the reading pipe we're going to pass in is going to be from the pipes array that we created, and it's going to be the C2 value here. So let's just choose that one for now. And then we're going to print the details, and this is nice initially because it kind of tells you what all these settings were that you have. So if you can't connect to your radio, these settings have to match up with the other radio that you have, short of like power amplification and stuff like that, but like data rate, channel, that needs to be set up the same on both Pis, and this allows you to actually see what you set up so that when you execute the script, you know what's going on. And then we're going to set up our radio to start listening, because this is the receiver, so the first thing it's going to do is wait for a signal to come in. This will be a simple script, so we're just going to create a while true loop here, and we're going to create an acknowledgement payload, and that acknowledgement payload will just be an array of 1 to, say that we have received something. And then we're going to wait, and we're going to wait until the radio starts actually receiving something. So that's what we're doing here in this loop, and this is why we need time, is just so that we sleep, and we'll sleep for just 1/100th of a second, and as soon as something starts coming into our radio, we'll break out of this while loop and we'll start doing something about it. And that something will be getting our received message. So we set up an instance like a blank received message, and then we're going to read our radio, and we're going to populate our received message with whatever the message is, and then we're going to have to get the dynamic payload size, that's a capital S. And so that populates our received message with whatever was sent, and then we can get a dummy print statement in there, and the dummy print statement will just say we received this, and what is that? That is formatting our received message. The way that this communicates is in bytes, like 8 bits to a byte. And so what that means is the only thing you can actually send through the radio is a integer value between 0 and 255. It's the same as 2 to the 8. You have 256 values that you can send. So you can't really send the letter A. You can send the Unicode encoding for the letter A, which is represented by a number. So if I just read out like number 100 to you, that doesn't really mean anything. And so we can't really interpret that as a string unless we decode it back into our standard Unicode characters. So what we're going to do now is we're going to translate the received message into Unicode characters that you and I as people can understand. Let's just push this up a bit. And we can do this with a for loop. So we can say, first we're going to create our instance of string that we can append values to, and then we can say for n in received message, we're going to decode into like what I considered a standard Unicode character set, and you can look up these tables online as to what value equates to what. So what we're going to say is if n is greater than or equal to 32 and n is less than or equal to 126, which is just an arbitrary range that I chose based off of the charts, we're going to add to our string the character equivalent, the Unicode decoded character equivalent of our n value, and then after that for loop is done, we'll be able to say print our string. And now we've received our message, we've printed it, and now we can write our acknowledgement payload. So write our acknowledgement payload. And what is our acknowledgement payload? It's ACPL that we created earlier, and then we just need to send the length of ACPL. And just for confirmation, so that we know that we've made it this far in the code, we can say loaded payload reply of that, whatever it is, and it is ACPL. Alright, excellent, and that's all there is to it. So this is all you need in terms of code for getting your receiving Pi set up and running. So let's give that a save. So now let's move over to our sending Pi, and we're going to have to open up an instance of idle3 again and get going programming. So as you can imagine, I mentioned how important it is that the initial settings are all equal. You can imagine how simple it is. You can just copy paste this over to the other one. Now it's a little difficult for me to do this because I'm doing it headlessly, so just give me a minute and I'll get this copied over to our sending Pi. You can type it out if it's too much of a hassle for you. Alright, so I created the NRF24L01 folder on my desktop, and into it I copied that lib_nrf24.py file that we downloaded from GitHub, and then I copy pasted the beginning part of receive Pi and saved it as send.py in that folder. So we'll be importing the same modules and packages as we did before. We'll be setting up our GPIO the same. We'll have the same addresses saved. We'll be setting up our radio in the same way since we wired it the same. We'll have the same payload size, same channel, same data communication rate, same power amplification. All that will be the same. The only thing that we are going to have to change a couple things here. This is our sending Pi. It is not our receiving Pi, so we don't need to open up a reading pipe. Instead, what we need to do is open up a writing pipe. And you can probably guess, since the reading pipe on the other Pi was pipes 1, address 1, and this is the same pipes, the writing pipe is going to be that same address, so that we are writing to that same address, and thus the other end receiving on that address will actually receive our message. We also don't want to start listening, because if you're listening, you're not sending. So you're doing one or the other with these transceivers, so we're not going to be doing that for that reason. Again, it's a simple while true loop that we'll be writing here. This will be one-way communication, and knowing that our payload size is 32, it means that whatever string message that we send has to be 32 or fewer bytes in length. And so ours will be hello world, which fits nicely within the limits of what we're allowed, and then we're just going to send using radio.write our message. The message has to be in the list format, by the way, like an array, so this will break it up into the values HELLO, which will then be converted into their respective numerical value for transmission. So then we'll say, after that's done, we'll print a statement that says we sent sent the message of blah, and that is our message. And then we'll check if it returned a acknowledgement payload. And the way we do that is if radio.isAck payload available, what a convenient function, right? Our returned payload will be equal to like a blank array for the beginning, and then we will write to it. Now, this will be there. It's reading now, and it will be reading if there is something sent to it only. So like if there is nothing sent to it, it won't pick anything up. And so we'll be updating our, sorry, not returned payload, but returned PL for return payload. And then we will be pulling the get dynamic payload size. And then we'll just print out what our payload is. So our returned payload was blah. Okay, great. Otherwise, if we didn't get it, then we'll say print no payload received. And then, since we will be sending this message, we don't want to like massively spam the receiver, so we'll just put in a 1 second sleep here so that you know, we don't flood up the terminal with too much. So let's give that a save. Now in theory we should be able to execute our scripts and get messages received. So going back to, too far, let's go here. Okay, so this will be our receiving computer. This is the one with receive.py. So to execute our script, we'll type in sudo python3 receive.py. Alright, so there's a bit of a typo here in our script. It's not enabled, it's enable. So let's correct that. And since I copy paste this between both receive.py and send.py, I'm going to have to change that. So I'm sorry, that's a bit of a typo. That's what happens when I write such a long script on the fly. So let's try that again. So again, the file is receive.py, so sudo python3 receive.py. And there we go. So what this is in front of us is we have like our transmission and receiving. We have our transmission address, receive address, and we have our CRC length, the model, the communication rate. That's what I'm talking about. Then you see it's blinking. So what is it doing right now? It's probably sitting, hopefully it's sitting, in that loop that is waiting for something to happen. So going over to the other Raspberry Pi, this is the send.py. So sudo python3 send.py, and it displays the information again, and then you see here, so we sent the message of hello world, no payload received. We sent the message of hello world, and then we got a return payload of 1, and it's doing this every second. Cool. Well, if we're getting a return payload, then it's pretty safe to say that we're actually receiving our message. And here's our received message, and this is updating. As you can see, it's scrolling at an interval of 1 second. What we're actually receiving here is the Unicode, like the numerical values for our message hello world, which is then being translated into the string hello world. And there you have it. Simple one-way communication, aside, well, if you ignore the whole like payload reply, simple one-way communication between two Raspberry Pis communicating with strings using a NRF24L01 plus transceiver. Now this is all well and nice, but it's kind of simple and not very practical. I mean, one-way communication has its merits sometimes, but what happens if we want the other Pi, the receiving Pi, to actually do something? So in the next tutorial, I'm going to show you how to set up like a master-slave setup using the NRF24L01 plus, so that you have your master that calls the shots and the slave does something, like for example pulls sensor data from a temperature sensor. So I'll see you in that video.